Hi, in this video I'm going to be covering chapter 6.1 to 6.3 from our textbook. This video should be helpful because I am not going to be present October 22nd, 2019. And so I hope that by you watching this video and then referring to the textbook and maybe other resources that you will be able to understand the quantum mechanics of chemical bonding. We're going to start by developing a common language and a picture. So suppose I have atom A coming closer to atom B. If they are very far apart, the internuclear distance, RAB, is such that there's hardly any interaction. And so the potential energy as a function of distance RAB is zero. As the atoms move closer together, the energy decreases. But we find that there's an ideal distance known as R equilibrium. And at that distance, we get the minimum in the potential energy as a function of the internuclear distance. If we get any closer, then the repulsive forces between the nuclei make the potential energy go up. Now, one of the questions is, so we have this maximum decrease in energy known as the E, but the bonding energy is known as D0. Why is that? Because if we think of a vibrational system, one in which the atoms can vibrate, and we think of the quantum mechanical states, we are going to find that the bottom state, which we're going to designate as V equals 0, is going to look like this. And it's going to have no nodes. But notice that it has a distribution such that it does not touch the bottom. If we had an energy equal to 0 and this position would be perfectly defined, it would violate the uncertainty principle. And so the bottom state is such that it has no nodes, and there is a difference here. The difference, dE minus D0 equals the 0 point energy, okay? And that 0 point energy is related to the uncertainty principle. Okay, now that we have a common language, we can start digging in. So imagine that each of these hydrogen atoms in the top are described by wave functions, 1s plus 1s. As we get them closer together, and if the wave functions are in phase, there's going to be constructive interference. And at some point, we're going to have the optimum distance, which is going to be defined by R equilibrium, where we have an optimum amount of electron density here, which causes the bonding, as we shall see. I wanted you to visualize this process, and as I alluded to in class today, one way to visualize this is to think of water drops. So it turns out that I found a video that is very, very useful. So in this case, we're going to consider each of these droplets of water, although one has a little bit of ink. We're going to consider the drops of water to signify the 1s wave function from each of the atoms. Then in this cool surface manufactured at MIT, where they can control how hydrophilic or hydrophobic the surface is, and they can use it to move the droplets, they're going to be able to push these droplets together, and we're going to be able to see how they form one drop, or basically this allows us to imagine, this is as close as I've been able to make it, to imagine how is it that two hydrogen atoms may form a chemical bond. And they fuse together. So now imagine that we have one nucleus here, one nucleus here, and now the new wave function encompasses the two atoms. Okay, the next picture in the book is going to introduce a concept known as the Born-Oppenheimer approximation. And in a sense, the explanation that the book gives, which is that the electrons are moving very fast and the nuclei are moving slow, is accurate. And we talked about this in class when we talked about the concept of reduced mass. If you remember, the reduced mass equals m1 times m2 divided by m1 plus m2. We found that if m1 is greater than m2, say about a factor of 10 or more, then the heavy mass doesn't move. Okay, that's the Born-Oppenheimer approximation. And so we can imagine that the nuclei are going to find their equilibrium positions slowly and the electrons will adjust. Now, I do not like to think in terms of classical particles because we're talking about quantum mechanics. So instead of trying to imagine electrons, which is completely the wrong picture, we should start imagining a wave function that might include the new arrangement of electrons that best suits a particular geometry. Now, if you want to have a more pictorial analogy of the Born-Oppenheimer approximation, you can think about the following. Okay, so what we have here is a classical pig. And now imagine a cloud of flies flying around it. Okay, so these flies adjust very quickly to the position of the pig. So in a sense, we don't need to worry where all the flies are. We know that if the pig moves from one spot to the next spot, the cloud of flies will follow it. So the same thing with the Born-Oppenheimer approximation. Now, it turns out that there is a problem that we can solve quantum mechanically exact, and that is the case of the molecule H2+. We can solve it exactly because there's very, very few parameters. We only need how the only electron interacts with this nucleus and with this nucleus. So because we have positive and negative charges, the attraction is going to be coulombic. So we have Coulomb attraction, and therefore we have a negative sign, right? It lowers the energy, and that comes from the electron nuclei position. Then we're going to have repulsion that is going to depend on the internuclear distance, and because it's repulsion, it's a plus, and we only have one term. This case, especially for fixed nuclear position, we can solve exactly. And then we can solve it as a function of internuclear distances, and we can get the wave functions, which is really, really cool. So we can now see how the wave functions for molecular orbits look, or molecular orbitals. Here we go. As we could imagine, the lowest energy orbital has no nodes, and is designated as sigma. The next higher energy level is going to have one node, and that will be designated as sigma star. So we have the first sigma, and then we have a designation of G. G stands for gerade, and you can think of this as symmetric. And then U stands as ungerade, or asymmetric. So here we see that the wave function does not change phase. There's no nodes. Here we see that the nodes change sign, and therefore it's an ungerade state. Okay? Now, gerade goes according to the internuclear distance. Okay? Very well. We know that if we wanted to do chemical bonding, we sometimes use these diagrams called correlation diagrams. For example, the correlation diagram for hydrogen might look something like this. So now we can think of, here's the energy of the non-interacting systems, and then here's the correlation diagram. And so this one lowers the energy, this one increases the energy. Okay, and this is how this relates to correlation diagrams. We can also think in terms of how does this correlate to potential energy diagrams. So again, here we have zero interaction energy. Here we have V as a function of RAB, so the potential energy. And now, when we're very far, we have zero interaction, then we have bonding, okay? But if the wave functions have a different phase, we would have the anti-bonding, okay? And finally, how do potential energy diagrams correlate with correlation diagrams? Well, at our equilibrium, we can draw this point in the potential, and then we draw the energy levels like this, and we make a correlation diagram. So as you can see, these wave functions are associated with an equilibrium distance. They can be shorthand noted as a correlation diagram, and they are representing one point in the potential energy curves that define molecules. Okay? Excellent. So look what we have here. We have the exact calculation of what is the potential energy as a function of internuclear distance for the molecule H2 plus. We see that the 1 sigma G and the 1 pi U are represented, and if we draw a line at our equilibrium, we see that the gain in bonding is not as large as the gain in anti-bonding. That means that if you have 2 electrons here and 2 electrons here, you're not going to be forming a bond. Okay, very well. Again, this is designated 1 sigma G, 1 sigma U star, and this is the internuclear distance in terms of Bohr radii. So now let's see how other higher energy level molecular orbitals look. We started at first with the 1 sigma G, and that would come from the 1s electron. So we have 1s and 1s. We can draw a quick correlation diagram, and we get the 1 sigma G and the 1 sigma U star. Then we can think of the 2s levels, draw our correlation diagrams, and we find that the 2 sigma G, so here we have one node here. Here we see another node, right? There's a node there, kind of like a radial node, like belonging to the sigma to the 2s. And here we see 2 nodes, one node like this, and then one node in between this one. So here we see 3 nodes. One, yeah. So this is actually two nodes. Two nodes. One we can think of as going like this. Okay? Very well. What are the next energy levels? Well, the next would correspond to the two p orbitals, right? So we will have the following. We have the 1 pi u, and this will be two of them, because there will be two different planes that we can have this. In this case, this one is drawn like this, but there's going to be another plane that is, so that would be the x-axis. There could be one in the y-axis. Okay, so there's two of these orbitals. Then there's going to be the sigma g. There's only one of them. Then the pi g. And then finally the 3 sigma u. We can see in here two nodes. Here we can see this node and this node too. And then we can see this one and then this one, or whatever you want to draw it as. So these are the different nodes, and this is why, as you have more nodes, as the wave function needs to make more wiggles, it has more energy. Okay, so this will be the correlation diagrams, and this is what we find for H2 plus. As we will see, these correlation diagrams and these molecular orbitals remain exactly in this order until we get to nitrogen. After nitrogen, they change slightly, and that's a topic that we will discuss the following week. So let's take a quick summary of what we have learned. We have learned about the Born-Oppenheimer approximation, basically that flies move much faster than the cow or the pig, and so they just follow, and that's what electrons do. So when we bat a ball, doesn't matter how hard we hit it, the electrons move right along with the nuclei. It's not like you kick and then all the nuclei move and the electron cloud lags behind. Then the next thing that we learn is that the solutions to the H2 plus case are wave functions called molecular orbitals. Those molecular orbitals are known as sigma, p, pi, and delta, which, if you remember from atomic orbitals, this come from S, P, and D. And that's, so from S, P, and D, that's where they got sigma, pi, and delta. Very creative. Then that bonding implies greater electron density between the nuclei. The nuclei, if you remember, are positively charged. So if you put negative electron density between them, then you allow them to get closer. We found that bonding and antibonding orbitals exist. Not only bonding ones, also antibonding, and they play a very important role. And we will learn to designate how many bonding and how many antibonding. And if you have more bonding than antibonding, then you have a chemical bond. Otherwise, you don't. Okay, we learned that sigma molecular orbitals are cylindrically symmetric around the bond, and that pi bonding and antibonding have a nodal plane. That means that they are not cylindrically symmetric around the bond. Now, there are attempts to try to explain in a little bit more quantitative way why is it that chemical bonds form. And that theory is the linear combination of atomic orbitals. In its lowest approximation, we will only assume that we have one atomic orbital for each of the atoms, and we're going to try to reconstruct, for example, H2 plus, but this time a little bit more quantitatively. I'm going to start with a non-interacting case. In the non-interacting case, I'm going to have that I have one s electron plus another one s electron. Okay? So one it comes from A and the other one from B. Then, when I calculate the probability density, so I'm squaring, and then in this case, we see that I have one sigma s squared and the 1 sigma s from B squared, and we get this interaction, okay? This interaction we get because they're pretty close. However, we know that if we get more electron density, we will have bonding. If we have less electron density, we will have anti-bonding. So let's see what happens next. So in the case of bonding, I have the 1s plus the 1s, and then when I square, what is it that I get? So let's do a quick math reminder here. So this is just math. I have a plus b squared equals a squared plus b squared plus 2ab. If I have a minus b squared, I get a squared plus b squared minus 2ab. What is it that I learned? That here this term plus 2ab has led to increase electron density and hence bonding. When I go to the minus case, I have the minus 2ab, which leads to anti-bonding. Okay, so linear combinations of atomic orbitals are very useful for us to get an idea of where does bonding come from. Okay, so now we can get a full picture. Here we have the 1s orbitals coming together to form a new wave function. This new wave function is known as sigma g1s, and in this case it's a bonding wave function. In this case we have the wave function known as sigma star u1s, why u? Because it's antisymmetric. Okay, and we see that we get bonding, we get an internuclear distance that is ideal, and then we can imagine that d0 is going to be here, and we can see that there's the anti-bonding case. We see that at internuclear distance we're going to have this energy for anti-bonding, this energy for bonding, depending how many electrons we're going to put here. Perfect. So look at this. We are able to use linear combinations of atomic orbitals to calculate the bonding for H2 plus. We find those calculations are the dashed line. We see that the dashed lines are not exact, right? The exact solution is the solid line. Okay, so this is the anti-bonding, this is the bonding. And so why is it that the linear combinations did not give us the exact solution? Well, because the atomic orbitals that we're using are very good at describing atoms. They're not good at describing molecules. So when we only use one atomic orbital, we get very poor results. The cool thing is that we're able to add more and more and more orbitals to get better and better accuracy. And modern calculations add thousands, tens of thousands, and even hundreds of thousands of atomic orbitals because computers are so fast that we can keep optimizing as much as we want. Now, let's look a little closer at the correlation diagrams for the first row of diatomics. Here, we're going to be discussing H2 and maybe helium-2. So we see that there's going to be some bonding and some anti-bonding. And now we're going to use the Aufbau principle to fill the electrons. Okay? So for H2 plus, we have this case, and we see that we have the electronic configuration, sigma G1s, 1 electron. The bond order is going to be a half. We see the bond energy and the bond length. When we go to hydrogen molecule, we see now 2 electrons here, a bond order of 1, much stronger bonding energy, and a shorter bond length. When we go to helium 2 plus, we now have 3 electrons. We now have 1 electron in the antibonding, so this corresponds to helium 2 plus. The bond order is a half. We see that the bond energy is about the same as before, half a bond order, half a bond order, except that this one was a little bit more bound. You see, there's a little bit of a difference between antibonding and bonding. And the bond length is about the same as before, however, just a tad longer. Finally, when we go to helium 2, we see that the bond order is 0, and therefore there's almost no binding energy, and the bond length would be very, very large. What is going to happen as we go to second row diatomics? Well, in this case, we see that from H2 plus all the way to nitrogen 2, we're going to see this arrangement, okay? Now, you may ask, what happened to the 1s? Are they going to form sigma G1s as well? And do we need to worry about those correlations? The answer is not. We don't worry about the 1s's. And the reason is that the 1s orbitals shrink quite a bit and they don't participate in bonding for a second and higher row diatomics. Okay, so now we go, for example, for nitrogen, and we see that we have 2s electrons being contributed from both sides. One goes here, one goes there. Well, doesn't matter how you portion them. The idea is that this is all filled, no bonding. Then we put all of these electrons in here, and we end up with 1, 2, and 3. So the bond order equals 3. Here you see the pi u's in the x and y coordinates, and then we have the sigma 2pz above it. Interestingly, once we go to O2 and greater, and that is everything else in the periodic table, O2 and greater Z, is going to have a different order here. Okay? Before it used to be like this, now it's like this. And the reason for this, we're going to explore the next week, okay? I just wanted to show you this because now there's no bonding for the 2s's. Here we have 3 that are bonding, 2 that are anti-bonding, so the bond order here equals 1. We will be talking more about second row diatomics and heteronuclear diatomics next week. I hope this video has been useful. See you on Thursday in class. Take care.